Can the flap of a butterfly's wings really start a hurricane on the other side of the world? It sounds poetic, even impossible. But this simple question lies at the heart of something called chaos theory. Chaos theory isn't about disorder or randomness. It's about how tiny changes in the starting conditions of a system can lead to massive and unpredictable differences over time. In other words, even when a system follows strict rules, like weather patterns or the economy, its future can still be impossible to predict with perfect accuracy. Today, we'll explore what chaos theory really means, how scientists discovered it, and why it changes the way we understand, well, almost everything. My name is Frederick Christensen. Welcome to Geeka Nerdy. The story begins in the early 1960s with meteorologist Edward Lorenz. He was running weather simulations on one of the first computers, massive machines that filled entire rooms. One day, Lorenz restarted a simulation but rounded one of his numbers slightly differently, something as small as 0.506 instead of 0.506127. When the simulation finished, the result was completely different. That tiny rounding error had completely changed the outcome. This became known as sensitive dependence on initial conditions, and it's the foundation of chaos theory. Lorenz's equations described what we now call the Lorenz Attractor, a pattern that looks like a butterfly's wings. It's not random. It's deterministic, meaning it follows exact rules, but even so, it never repeats and can't be predicted far into the future. This shape became a visual symbol of chaos, beautiful, structured, but infinitely sensitive. We see chaos in everyday life. Take the weather. We can forecast it accurately for a few days, but after that, even tiny measurement errors make long-term prediction impossible. Or the stock market. Every investor's action affects prices in complex ways, creating patterns that are deterministic, but practically unpredictable. Even traffic systems can become chaotic. One small slowdown on a highway can ripple backwards, creating massive jams, a perfect example of how little changes amplify through time. Chaos also gives rise to fractals, infinitely repeating patterns that appear both in mathematics and in nature. Look closely at a fern leaf, a coastline, or a snowflake. They all show self-similarity, the same pattern repeating on different scales. It's chaos and order dancing together. Even simple mathematical rules, like those in Conway's game of life, can generate endlessly complex behaviors. Just from basic starting conditions, that's the magic of chaos. Order emerges from simplicity, but it never stands still. Chaos doesn't mean randomness. It means extreme sensitivity. It reminds us that even when systems are built on simple rules, we can't always control or predict what comes next. From weather and ecosystems to economies and even our own lives, small choices can have enormous, far-reaching effects. Scientists and mathematicians are still exploring the boundaries of chaos today, trying to understand how complexity arises from simplicity and how tiny moments can shape entire worlds.